Hi guys, in this video we will look at conformations of alkanes. Now in a subsequent video we'll look at similar information for cycloalkanes. Specifically we'll focus on cyclohexanes, but that'll be later. First we want to make sure we know a definition for conformer or conformation. Both of these terms mean the same thing. Here's your working definition. I will try to do some demoing some models here. I've got a smaller model than I use in class. Conformation just basically it results from when you're able to rotate a sigma bond. And sigma bonds can be rotated. I used two reds here. These are opposite to each other. We'll later call that anti. That would be the anti-conformation. But we can rotate this bond, and you see that the red moves sort of the same side here, and we'll later call that syn. So these are just different conformations due to rotating around a sigma bond. Now it's the same compound. It's not a different compound, okay? Let's sort of introduce some of this by showing this compound here. It's two carbons and then two substituents. Let's call those bromines, and let's sort of have a molecule . I mean, I could draw this molecule like this. That gives you plenty of information. We see complete formula. We see two H's on each carbon. If we join the tetrahedral nature of these two carbons and the H's, we would draw one forward and one back. And so for this carbon we have two bonds in the plane, one forward, one back, tetrahedral. Over here, two bonds in the plane, one forward. Now these two are sort of coming this way. We want to put the other two more up in this area. And one forward. See, both of these are forward. That one's just more sort of up, and this one's more down. And then we can put the other one there, back. So now we have two in the plane, one forward, one back. Now we're starting to show more complete information about this compound. I also have the BRs drawn anti. We'll see that term later. And so if we envision this is the compound here, carbon-carbon bond. These are your two H's that I'm holding on to here. But I got the bromines. I need to rotate this bond. Now whenever I rotate a bond, I'm not always going to hold the bond and turn it. Instead, I may just grab over here. That's the same as if I rotated the bond. But now the bromines are opposite to each other about the plane of this bond here as opposed to there. And that's how I have it drawn on my paper. And this H is up. Okay, if I draw it like it's up, it's also a little bit pointing back or open here. This area. Got to be careful when say back. It's up. And the other one is.
I didn't get that. Could you try again?
No, I cannot. I don't know if that's going to show up well. Okay. Let's focus on the bromines here. And so now this is more of a perspective drawing. And if we look down here, I say A, different ways to show conformations, including stereochemistry. See, we included stereochemistry here with the dashed in bold. Okay, perspective. That's what I have here. Now if we go over to the handout and look at this page, we see a perspective drawing. Here, if you replace these two H's that are in the plane with bromines, you'll get what I showed you here. All right, so a perspective drawing of, just to clarify, this is 1,2-dibromoethane. Just to do a little nomenclature. All right. Now another way to show compounds is called a sawhorse sort of structure, much less common. You will not see that much at all, but it is worth sort of, you know, it might show up on some random, maybe, you know, MCAT or somewhere, but we're not going to use it much. Sort of, here's the carbon, and you're kind of looking, there's that carbon-carbon bond. This H is straight up, and this H is straight down. Now in my drawing, those would have been the bromines, okay, clearly anti to each other. And then these two H's, or if you consider that the plane, one H is to the right of the plane, the other's to the left of the plane. But that's a sawhorse, and you'll probably never hear me mention that term again. What we're going to need to be able to do is go from a perspective drawing to a Newman projection. And the Newman is another way to show this compound, okay? But instead of showing it like this, we're looking at that bond, the side of that bond. Instead, we want to be able to draw it looking down that bond, okay? And I reckon your view right there is looking down the bond. Here's the front carbon. You can't see the back carbon because you're looking right down the bond. See, if I turn it to the side, you can see both. And so this front carbon is eclipsing the back carbon, just like the moon might eclipse the sun in the sky. Okay? Can we draw it like this on the paper? And I'll do that. This actually might work out pretty good. I can see what you're seeing on my camera here. Can we draw that? And we do this with a circle, circle, dot, dot. A circle and then a dot in the middle. The dot in the middle is this front carbon here. And what do we see on this front carbon? I see a bromine going straight up. Okay, that's up. Bromine straight up. What else do I see on this front carbon? See an H coming down and to the right and an H coming down and to the left. So down and to the right and down and to the left. Now, the bromine I'm holding, that's actually back. Okay, you see how it's back? This carbon here is closer to my face, closer to me. I'm holding so in that back carbon, look at it, you can't really see that back carbon. This circle, it's back there, I can't see it, but I can see the bromine coming down as if it's, see, if I lean it up, I can see it connected. But if it's hidden, I only see it once it sort of comes out from being eclipsed. It's back there eclipsed, but we see it coming out, and so we draw that bromine not from this small circle in the middle, but from the rim. We can't see it back there connected to that carbon. Same thing for the H's. this H is coming off of that carbon back there, but we can only see it once it moves out from being eclipsed. Same over here. And these are the same, okay? Same exact compounds, drawn in two different ways, a perspective drawing and then a Newman projection. Professor Newman was at Ohio State, and he came up with this way to show compounds looking down a bond because, well, there's limitations here. This gives you a different look, and it helps answer additional questions. Very useful. So we need to learn how to draw and discuss Newman projections. Newman was at Ohio State back in like the 60s, 1970s. I actually worked with someone a while back who worked with Newman and had some stories about Professor Newman. Okay, bromines are anti here. Well, they're also anti here. Not only are these the same compound, I have the same conformation. Same conformation of same compound. Okay? Anytime we're doing conformations, we're always doing one compound can have many conformations. This is one compound we're dealing with. Now this is the same conformation. The difference is a different view of that conformation. This is a perspective view, but it's anti. This is also an anti-conformation, but it's shown in a Newman projection, looking down the carbon-carbon bond. Okay, this may actually work out with these small models better than I had anticipated. H back there. Okay. So that view versus side-on view. And understanding that the bond can rotate. That's the bond rotating. Again, I won't always turn the bond. Because this compound has free rotation. Okay? What else can we say here? Let's move along. Okay, I showed you how to draw a Newman. I'll do it a different way though, because I showed you by looking at models. Let's do this. What if you didn't have a model? What I would have done is I would have stood over here, because it's on the paper like that. Let's pretend like it's glued on the paper, okay? Because once you draw it, you can't start rotating it. I need to stand over here so I can look down the carbon-carbon bond. Okay, stand over here. Now if I stand over here, what do I see? Well, that's what I see if I'm standing over there. But, okay. So what I will do is I'll say, let's stand over here and look sort of right through there down the 1, 2, with one being closer to me, so one's in the front. Again, it's like it's, can you still see that? You're standing here looking down the 1, 2. Let's see if we can get there. What do I see? Well, I have two carbons. It's going to be circle, circle, dot, dot. Carbon 1's in the front. It's coming from the small one. What do I see? I see a bromine coming straight up. Okay, I'm going to get the same thing here. I'm just doing it without looking at a model. I see a bromine straight up. Now, keep in mind this H. It's coming up off the paper. That's what the bold means. if I'm looking down, what side is that H on? It's on my right. Let's call this A and B. Okay, A. Now if I'm looking down and that H is bolded, that means it's behind the paper. Behind the paper is over here. And that's to my left. Now we'll have to get some practice at this, but that HB is to the left. In class, I usually stand on a chair at the board and try to look at this. It's even worse on the board because I can't take that board and try to turn it and see, ask you to look down the paper. Let's look past carbon 1 and let's look back over at carbon 2. That bromine is going straight down. The bolded thing is coming off the paper. Okay, there it is coming straight up. If I'm over here, it's coming to the right. Let's call that C and D. HC is coming up and to the right, and the other HD is coming up and to the left. And that bromine back there is going straight down. It's in the plane. It's neither forward or back. We got the same thing as we did over here. This is A, B, C, and D. Okay, we'll keep doing practice on those. One thing we want to point out is, I think at this point, dihedral angles. The dihedral angle is an angle between two bonds that are on different carbons. The front carbon and the back carbon. It's called dihedral, meaning two. It's two planes. Okay, let's see if we can illustrate that. I'll try to use markers. Those two markers, that is a 90-degree angle between them. Okay. Or I can do it like this. I think it's better to do it like that. That's a 90-degree angle right here. Now what if I lift this up off the paper? Well, it's still a 90-degree angle. Do you see the angle still there? It is boom, boom, 90 degrees. But now it's a dihedral angle. I put it back down, everything's in the same plane. But let's assume that's one carbon down here, and then this bond is connected to another carbon that's up here, and there's a bond there. Okay? It's still an angle, it's just two different planes. The angle between a group on the front carbon and the back carbon, and that's a 60-degree dihedral angle here. And when we start talking about nicely staggered, the back bond will be 60 degrees between the two front bonds in terms of dihedral angle. Trying to show it another way there. We may refer to this down below. This is where the methyl groups on butane have dihedral angles of 180, 60, or 0. Here they're fully eclipsed. There they're gauche. We'll see these terms later. There they're opposite or anti. We can actually go ahead and make sure we know those terms. We've mentioned them before. When they're opposite, they're anti, and that's actually what we had over here, right? The bromines were opposite. The dihedral angle between the two bromines is 180 degrees. Not going to draw it, but if that other bromine came like this, it would be 90. But instead, it's double that, sort of linear 180. And anti is actually good. It's the best because the groups have more room. If you can see it in these space-filling models. Now in this example, the two groups are methyl groups, making it a total of 4 carbons and making it butane instead of 1,2-dibromoethane. Now when groups are sort of to the side of each other, that's called gauche. And that's actually, I believe, French for sort of to the side. Dihedral angle of 60 degrees in this case. When they are eclipsed right behind each other, like here's our, if we turn this back red straight up, the front red is blocking out completely the back red. Front bromine blocking them. Really, you can't even see anything in the back. These two H's are blocking the two H's in the back. The two bromines are blocking, so that is a fully eclipsed. Now if I turn it a little bit, you see that bromine back there? You can see the, okay? That's actually worse because the two bigger groups sort of clash with each other as sort of shown here. Now when we draw the Newman, we don't actually draw them right behind each other, or you would just not draw anything in the back. And if you didn't draw anything in the back, it would be very vague of what was back there. So we usually draw it to the side a little bit, but we sort of imply that the dihedral angle is 0 degrees. Of course, if the back was turned just a little bit, like that, well, now that's an angle of maybe 5 degrees between this one and the back one. Again, if we turned it like that, well, that's a dihedral angle of 90 degrees. Okay, let's go back up to a dihedral of 0, eclipsed. All right, so it's convention that we have to show the back. Okay, it's implied that it's 0. Okay, so we're laying some terminology, groundwork, some establishing some foundation terminology here. Now, let's look at rotating compounds and the first one on this graph here is rotating ethane. Now, I'm going to make ethane by removing the two bromines and saying, there we go. That's ethane. 2 carbons, and each carbon has 3 little H's on it. And these are drawn in Newmans. So the first one we're looking straight on. There we go. I can just set that right there. And all 3 of the H's in the front are eclipsing the 3 H's in the back. The only way you can see them is if we kind of turn it to the side a little bit and you see they're back there. And so that's fully eclipsed. Okay? And all these at the top up here are eclipsed conformers with implied dihedral angle between the 2 H's here of 0. Now in this diagram, they're rotating the back carbon, okay, now eclipsed is always higher in energy than staggered. We rotate the back carbon 60 degrees, or the bond 60 degrees, we get to that. That's lower in energy because the groups have more room. The H nuclei have more room. They're not eclipsing. So we go down in energy. If we rotate the back another 60 degrees, we actually get back to what? That may not be perfect, but it's back to eclipsed. And it's actually the same as what we began with. Even though this is now two different H's. Because what we're doing here is we're rotating the back carbon a full 360 degrees. We've rotated it 120. If we rotate the back another 60, what do we get? We get staggered again. Rotate another 60. We get fully eclipsed again. Close enough. I got a little bit of, I can see a little bit back there. It should be okay. Rotate the back again. We get staggered again. And then rotate again, and we're actually have now done a full 360 degree turn. And we're back to the original, where now the two H's that are straight up are the same two H's that were straight up over here. And so what we showed here was a number of conformations, either eclipsed or staggered. We only showed conformations arising from a 60-degree rotation. We could have showed every 1 degree rotation. 1 degree, 2 degree, 3 degree, 4 degree, 5 degree. While those are different rotamers or conformations or different conformers, we typically will only stick to rotating 60 degrees at a time. The key thing to note here is there's really only two different energy levels. Because ultimately these three are identical. And of course these two on the end are identical because they are the same. And then the three staggered are all identical. Two different energy levels. Now if we go back to two groups, now I could put the bromines back on. I might just do that because I don't have the methyls. I'm going to put the bromines back on like we started with. In the graph it's going to be two methyls and thus butane. We get the same discussion with 1,2-dibromoethane. Now these are shown below, the Newmans are shown below, the energy graph is shown here. We start with the two, if you want to call the reds methyl groups, we can do that. The two methyl groups are both straight up and they're eclipsing each other with a dihedral angle of 0 degrees, and that is the worst, with those being syn to each other. Okay? Doesn't say that here, does it? But that's syn. Syn, they're both up or the same. That is a type of eclipsed, and it's actually the worst, and that's the starting point, A, the highest energy. Now down here they're rotating the front carbon. We rotate 60 degrees and we get that conformation. So now the bromines are to the side, or the methyls are to the side of each other, and they're called gauche to each other. The dihedral angle between the two, okay, I can draw that dihedral angle. You do it like this. This is like this, and then the bromine is coming like, if I can draw it like that, right? Now, there it's all in one plane. In my model, this line is on the paper, but this one is up off the paper, two planes. But it's still 60 degrees. Okay. Now gauche is a type of staggered. The two groups are not eclipsing. Nothing is eclipsing. And that's going to be lower in energy than the first conformation, the syn or eclipsed. If we rotate the front again, then we get to there. And this is actually eclipsed. But it's not the two methyls or bromines eclipsing each other. Up here it's the H eclipsing the methyl. Now of course the H is smaller, so it's not eclipsing it as much. So I would call this only partially eclipsed. And that's not as bad as fully eclipsed. Okay? We can maybe call this full eclipsed. I'm going to call this partial eclipsed because the groups that are eclipsing are not the two big groups. So this conformation is not as bad as the original, but it's worse than the gauche. Because keep in mind, eclipsed is always worse than staggered, and gauche is a type of staggered. Groups are not eclipsing, so they're called staggered. Okay, if we rotate the front another 60 degrees, what do we get? Now the two methyls, or whatever you want to call these red groups, are anti, and that's the best. Okay? Turn to the side, you see they're anti. Best meaning lowest energy, and you see how D has the lowest energy here. Now if we keep rotating, we're just going to go back and sort of repeat. Rotate the front 60 degrees. What do I get? The H and the methyl are eclipsed. We call this partially eclipsed because they're not both large groups. And so E and C are the same. I wish they had called this sort of C prime, because it's identical to C, it's just a different H. Rotate another 60. Now we're back to staggered. The H's are, the bromines or methyls are to the side of each other, they're gauche. We can call this B prime. That is, the energy of the B's are the same. The B's are good, but not as good as D. And then if we rotate again the front another 60 degrees, what are we back to? We're back to the two large groups fully eclipsing, and they go back to A here, which I agree. Full eclipse, it's actually the original, just like A, and we did a full 180 degree turn on the front carbon. and we went back to high energy again. So in this case, how many different energy levels did we have? 1, 2, 3, 4. That's a repeat, that's a repeat, that's a repeat. 4 energy levels. And so that's the type of question we would need to be able to answer, at least one type, and to understand what's going on here. Dihedral angle here is between the two methyl groups. Of course, a 360-degree dihedral angle could be considered a 0 degree. Okay, so that's the traditional sort of energy graphing of conformations, full turn of one atom, one bond, with the structures drawn in Newman conformations. Okay. Let's do some practice here. Show the most favorable conformation of the compounds below. Looking down the 1,2 bond, you do need to have nomenclature. Keep nomenclature in mind. The 1,2 bond is going to be, that's 1, that's 2. You can name these compounds. That'll be carbon 1. I'll do one for practice, and then you can do the other 2 on your own, and we'll look at them later, perhaps in class. We need a circle. Let's also, I'm going to do it on different paper. Circle, circle, dot, dot. If I can draw a good circle, that would help. Okay. By the way, what is the best conformation? Largest groups anti. Of course, staggered. We can just say anti. Well, the way I'm going to do this, I'm going to draw it as I see it. Then I can rotate it if I need to. I'm going to pretend like I'm looking down the 1,2 bond. I need to stand over here. Okay. See, carbon 1 coming straight down is the F. Coming to the left is the chlorine, and there's an undrawn H on carbon 1 coming this way. In Newman projections, we want to always draw in our H's. That's the front carbon. How do I know the chlorine's coming to the left? Because if carbon 1 is in the front, I need to turn the paper this way. Carbon 1 is closer to me. That chlorine is dashed. It's behind the paper. If I turn the paper like this, behind the paper is on my left. Chlorine's on my left. By default, the H, which is coming forward, is on my right. Now we can look at the back. Coming off of carbon 2 is this ethyl group going straight up in the plane. 1 carbon, 2 ethyl group. The other 2 atoms on that carbon are H's. Well, that's easy. You can put an H on each side. We saw up here nothing was eclipsed. Those H's belong here. Everything is staggered as drawn. That's actually why we draw usually zigzag. That leads to everything being staggered. Okay. The question is that the best conformation for this compound? What's the largest group on the front carbon? Chlorine. It's a larger halogen. What's the largest group on the back? Ethyl. not H's. Right now, the two largest groups are gauche to each other with a 60-degree dihedral angle. That is not the best. The best is when these two groups are anti. Well, we can rotate these. To rotate them on the paper, just do that. We can take this front carbon and turn it. Okay? Just like if I took this front carbon and turned it. Okay? The bond is not moving, but the two H's and the group, the other three bonds, will turn just like a clock dial. I'm turning it counterclockwise, or I can turn it clockwise. Okay? I'm going to turn it counterclockwise because I want the chlorine to be down here. And so the F is going to go here, and okay. That usually indicates that I turn something. I can draw a circle. I did not turn the back carbon, and so those are the same coming off the back carbon. The front, the chlorine is now straight down. Okay, I just took this and here, the chlorine is now straight down. And the other groups, they just turn. The F moves here, and the H moves here. And now we have larger groups anti. The ethyl and the chlorine. And that is what we predict to be the best conformation of this compound. Now we can ask questions. For example, what is the dihedral angle between the F and between the fluorine and the ethyl in the best conformation? 60-degree between F and the ethyl group. Or we could ask any other questions about that. Dihedral angle. Two different planes. Groups are on two different carbons there. Okay. You try the other two on your own. Couple of miscellaneous things to finish up here. Question, can a syn or gauche conformation sometimes be preferred? And actually, yes, for this compound, gauche is more preferred, not anti. Can we come up with any reason? Okay. Again, usually anti is the best. Why is gauche the best for this compound? Think about it. F. Is intramolecular H bonding possible in the following compound? If so, illustrate that. No need to use a Newman projection. Okay, think about that. I want you to have some time to think about these. That's the best way for you to sort of learn what I'm trying to get at here. Now also, we want to be able to go from a Newman projection back to maybe some type of regular line bond or perspective drawing. And that's sort of kind of what you need to do here. Ultimately, the question is, can you name these compounds? I'll do the first one for you. I'm looking down a carbon-carbon bond. On the front carbon, I see a methyl group in the plane. See a bromine to my right. If I'm over here, and the bromine is to my right, it's going to have to be coming up off the paper. So it's going to have to be bolded. And then the 1, 2, 3, and then the butyl group is going back. 1 carbon. I'm in the way. 2, 3, 4. 1, 2, 3, 4. Then the back carbon, I see 2 H's and an F. Well, I'll give you a little heads up. If you have 2 H's, we don't really need to worry too much about stereochemistry, because the carbon is not chiral. That's what I see. I can clean this up. 2 carbons and an F. This carbon has a 1, 2, 3, 4. I really need to keep stereochemistry here though. Let me do this again. F, boom, boom, and then the methyl. I need to maintain that stereochemistry. The bromine is going to be forward, and the ethyl group, butyl group, 1, 2, 3, 4, like that. There it is, cleaned up a little bit. I still don't like it because I would have preferred to put the larger group in the plane and put the methyl forward or back. But it doesn't matter, and that's not how it was drawn. Can we name it from there? Longest continuous chain, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Looks like a hexane, but which one? 1, 2, 3, 4, 5, 6. The one with most substituents, right? Is that how we decide here? One with most substituents? It's actually in the same handout. Yes. Longest chain, if there's a choice, go with chain with most substituents. That would be, this carbon would be included. In terms of numbering, this is going to be 1, 2, 3, 4, 5, and 6, because in this way we have a substituent at the 1 position. Alright, we have a hexane. What is on the hexane? A fluoro, a bromo, and a methyl. Alphabetical order. 2 bromo, 1 fluoro. F-L-U-O-R-O. 2 methyl. All one word. 2 bromo, 1 fluoro, 2 methyl. See, there's the methyl group. Don't forget about it. It was not part of the longest continuous chain. There's your longest continuous chain. Methyl at the 2. Alphabetical order, BR, F, methyl. Look good? I think so. So we named the first one. You can try naming the second one. I really encourage you to be using your textbook here. Of course, always, but particularly here, I think you'll see some more drawings to help you visualize the stereochemistry a bit. So if you haven't been using your textbook, I urge you to do that. Okay guys, in the next video we will look at conformations of cyclohexanes and do this material here. Okay guys,